Ladies and gentlemen, welcome to room 9 for the next session, Git Under the Hood. And please have a welcome to Babić.
Thank you. Thank you, and welcome again to Tech Days 2022. It's amazing to be here again. I've really missed this, and I'm really glad that I can be here today with you and present this topic to you. The topic is called Git Under the Hood, and I will say a word or two about why this topic, and then just for introduction, my name is Babić or Vjekoslav Babić, whichever you prefer. Both are equally probably complicated. I've been a member of this community for a long time. I've been delivering sessions here, and you who know me from earlier know that I've usually presented stuff on the cutting edge of things. So I guess I got demoted this year. Let's take a look at why Git. It's very interesting, like why am I here talking about a 17-year-old concept? And this really does feel good, bad, or strange. I did an experiment a couple of years ago at Directions. I proposed a Git session just because, you know, they asked for more content, and I just said, okay, I can do this without too much preparation. And I didn't expect it to actually cut into the content, and it did. And after that session, I got quite some comments from partners asking for more, saying like, can you do this for us? Can you repeat this? Can you whatever? And then I started doing webinars, maybe some. Is there anybody here who has been to my Git webinars? Just clap your hands. Or, yeah, a few, yeah. So I've been doing this for like intensively for a year and some now. And what I've realized is that even though this is 2022 and the product is 17 years old now already, it is still relevant because we are all using it, and we probably are not the best kind of users of that tool. So when trying to explain with pictures, and you might know that I like showing pictures, let me say that in our pockets, all of us carry a device that looks like this. And this device has more computing power than NASA had at its disposal when they put the man on the moon, every one of us. On this device, we have at our fingertips access to far more information than Bill Clinton had through all of his intelligence agencies at the height of his presidency. And yet, statistically speaking, what are most people using this? Well, watching videos of cats. And when it comes to Git, we are not too far from that. Like, Git is a powerful tool. It is an amazing tool. It can do so much for us. And one of the goals of my session is to demystify Git, to bring it closer to you, to make it a part of your arsenal, to make you a better developer. Because I don't see Git just as some dummy content tracker sitting out there and keeping track of the code that I write. I actually see it as a development tool. And it helps me in my everyday work, and I hope after this session you will see it in the same way. So that much a little bit about why Git, and then let's start talking about what is Git. I think that always the best way to describe a product is if you ask the product to describe itself. So Git says this: Git is a stupid content tracker. And if it sounds silly to you, this is actually the first thing that you will officially read about Git if you go to gitscm.com, which is the official Git website. There is further down like a definition that kind of tells a little bit more what Git really is. And let me read it. Git is a scalable, fast, distributed revision control system with an unusually rich command set that provides both high-level options and full access to internals. Wow, a mouthful. And there is something that I would like to highlight in this slide. That is that Git is actually a command line tool. And I would like to break a conception that many developers have that Git is some service running on your machines, watching over your files and your folders. It is not. It only reacts when you invoke it. When you call a command, then Git does something for you. But it doesn't keep an eye on your code or anything. It does not care. Only when you care enough to ask, it will care enough to answer. So how do we ask Git to do something for us? Well, again, if you ask Git documentation about what kind of commands are there in Git, there are two kinds of commands. there are these nice, shiny commands that Git calls porcelain commands, like things that you might even know, like git clone, git push, git merge, stuff like that. And then underneath, we have other kinds of commands that Git calls plumbing commands, stuff that you probably never did, like git reflog, git cat file, git hash object, etc. So these are those dirtier commands which are running completely deep under the hood, intended for the tools to call them. But both of these kinds of commands serve the same purpose ultimately, which is to you get a picture. It's just that these here are, you could say, user-friendly, and these other ones are more for professionals. So now that you've seen that we have these two kinds of commands, let's try to see what is the most common thing. Like, of all operations that Git does, invoked from any of these kinds of commands, what is the most common thing that Git does? So to be able to answer that question, we really need to go deep, deep down under the surface. We need to dive as deep to the bottom as possible and see how Git actually works. Was that Waldo? Okay, that guy. So at the bottom of things, when you go all the way down, Git is actually a dictionary. And when I say dictionary, I think that all of you should be familiar with what a dictionary is. Like, we have these kinds of things in AL, like a dictionary of text Boolean, or dictionary of date integer, or dictionary of GUID decimal. So every dictionary is a key value pair collection, where key is unique, obviously, and then there is some value, which kind of depends on that key. So talking about Git, and knowing that Git is in its heart a dictionary, what is key and what is value for Git? So let me start from value. Let's take a look inside of this dictionary. Value is any sequence of bytes. And this is really important because there is one other misconception about Git, that it's actually not good in handling binary. Git handles everything as binary. For Git, everything is binary. Your text is binary. It's us that have problems with binary when we do strange things. But that's something that we can talk about later. In any case, for Git, everything is binary. Every value is a sequence of bytes. That's how Git sees values in that dictionary. So if this is the value, then what is the key? The key is SHA-1. So what Git does is every single time there is something for it to store in that dictionary, it will actually first calculate SHA-1. So how does Git do that? Let me start by showing you first demo. There is this command called git hash object, one of those, professional commands that run deeply under the hood. You probably will never need to call this command yourself at all, but trust me, Git runs it all the time. So let's take a look at this screen here. I'm just going to hack a little bit into Git, and I'm using git bash for this, and I'm just going to type echo, and then where's Waldo? And then I'm going to pipe this thing into git hash object. And I'm going to use standard input, because hash object otherwise works with files. So I'm just redirecting my input to this, and then I get a SHA-1, or a hash. So this string is converted into this hash, and when Git stores this string, if it needs to store that string inside of its dictionary, it will be first converted into, or actually hash will be calculated, and then Git will handle it. And if I, for example, go here and I say like something like right here, and then run this, it's a different hash, different SHA-1. And then if I repeat the first one, I'm obviously going to get the exact same one that I got the first time, because for SHA-1 algorithm, the same input obviously always gives the same output. And now something important here is you can see that here I have PowerShell open as well. And I earlier said that Git actually operates on binary level, not on text level. Let me do exact same thing in PowerShell to see who is better, PowerShell or Bash. Echo, where's Waldo? And then I'm piping that to git hash object standard input. And when I run that, I will get a different SHA. So why is that? And you know, if you try it on your machines, you might get the same, but if you run Linux or Mac OS, you might get yet another SHA. So how can it be that the same input provides the same output when it obviously doesn't? Well, it's about binary, because Bash works on UTF-8 level, which is not injecting anything, whereas PowerShell works on Unicode UTF-16 little endian, and then injects something at the end, which Bash doesn't. And that's why you will get a different different output, because it seems to be the same input for you, but on binary level it is not. However, let's take a look at this file. The file contains exact same content. So if I do it with file, because file is on binary level exactly the same for Bash and for PowerShell. So I will just go from PowerShell and I will say git hash object, and then I will pass this where's Waldo, and I will get this familiar SHA which starts with 5.2 or whatever. And then I will do the same from Bash. I will just do git hash object, and then where's Waldo, and I should get the same, because on binary level this is the same file. So the point here is that with this algorithm, with this approach, Git is always able to identify equal content equally on absolutely every machine out there. So if every of us in here in this room had this file on their machine and they would process that through Git, we would all get exact same SHA, and this is very important. So I've said that Git is a dictionary, but Git is not just any kind of dictionary. Git is a persisted dictionary. So it actually has this -w, which stands for --write, which allows you to actually write or commit, or not really commit, but I'm apologizing, don't blame me, I'm full of Git terminology and I cannot. So git hash object -w will persist whatever input is in this dictionary. So let me try to do that. I will just run the same command and add -w, and it fails. Why it fails? Well, I can run some Git commands like this one without being actually under Git source control. But if I want to store something in Git's persisted dictionary, I actually have to be inside that dictionary. So I need to initialize this repository. So I will do this. I will just say git init, and this is now initialized my repository. And an invisible folder has appeared in my demo1 folder in this case. And let me actually make it less invisible. I will just do user settings and then files, ignore. No, it's not ignore. Yeah, exclude. Yeah, apologize. Files exclude, and I will just delete this git. And when I do, git appears here. And then if we take a look inside this git, we can see a lot of things. I do not recommend that you really modify anything manually, but we will spend a lot of time in this folder just to understand what is going on under the hood. So when I have written this object, there is this objects folder. I haven't written anything yet, actually. I've just attempted to write. But when I try to write again, now that git init has been executed and I'm inside of a git folder, when I run this, now this has been written, and if I refresh this, I can see that there is something in there. And let's not yet talk about what that something is and why it is like that. Let's first try to see and understand how this git hash object works. First of all, it takes the content. So in our case, this is where's Waldo followed by this line terminator. And then when we execute git hash object, what Git does is it takes that content and then attaches a short header to that content. In this case, it says blob because it's going to store a blob. And then it says what is the length of the content being stored. And then it attaches this ASCII 0 character or Unicode 0 character as a delimiter. And after that, it attaches the rest. And then it calculates the hash not from the original content, but from this. And then when it has hash, It wants to be efficient. So it actually compresses the content, everything, like the header and all. So when it's done, what it does then is it splits the hash in two. Takes the first two characters, creates a folder if it doesn't exist. And then the remainder of SHA is the file name. And then it stores the content, compressed content, into that file. So let's take a look at this a little bit. So now we can see that we really have this file here, 52, and then the rest, exactly as we expected. Now we know why this happens and what will happen if I, for example, change this and I say, where's Waldo? Right here in the front row. And then I go and... So now that I have this file, where's Waldo.txt, and when I run this, I would expect that, of course, this would be overwritten. I don't need this anymore because file is this, and so Git should overwrite, but it does not. It actually creates another one. Okay, let me try again. Let me say like, okay, sleeping. And then I run it again, and of course, I will get another one. So here I have yet another blob object in my Git repository. So why is that? That is because SHA is an identifier. It is the identity of the content. So when Git calculates SHA, it knows that there is no possibility. I mean, there is theoretical, far remote possibility that, under some very unlucky circumstances, there would be the equal SHA. It has never happened and probably never will. We can discuss that in Q&A. So when Git calculates SHA, it knows that in the entire universe, every other object will have a different SHA. So it can really relate, this SHA belongs to this content and vice versa. They're just connected. You cannot detach one from the other. So when you save a new object or store a new object in this Git persisted dictionary, it will always create a new entry in there because it's always going to be new SHA for new content and old SHAs remain for the old content. So all objects in this dictionary are immutable. This bond between SHA and content is unbreakable. It is always, it's forever. And there is a name for this thing. This thing is actually called content addressable storage. And Git is not the only thing out there that employs this principle. And it is just a lucky coincidence that when Git was being invented, this content addressable storage was quite a hit because of the financial industry that had exact same requirements. And then Linus Torvalds, who was designing it, actually chose that as an amazing principle. And the consequences of this choice to design the system like this, that everything is identified by a SHA, and then you have this unbreakable bond between the SHA that actually tells you the content, are so far-reaching that you just cannot imagine how much optimization can happen because of that. For example, I save another file elsewhere in the system, but if it's the same content, guess what? Git doesn't need to store it again because it already has it. It's the same SHA, so no need to store it again. You push objects to remote. Remote knows the SHA. Okay, no need to push that object because it's already there. And others, as we will see as we go. So this is a little bit about this Git persisted dictionary. Let's go on. Let's talk about this not so stupid content tracker. One of major misconceptions with Git is also that it monitors your code, as I said earlier. Like, people often think that, yeah, I'm working in Visual Studio Code. The moment I change something, Git tells me, okay, look at this file is new, or this file was deleted, or whatever. And then you think that Git is monitoring your code, but Git isn't. It's Visual Studio Code that monitors. So Visual Studio Code has a file system watcher running over your entire repository, and then when something changes, it actually runs some Git commands underneath, and then parses the output of those commands to present them to you in a friendly way. But this is not Git doing these things. It's the tools that do those things. So Git does not really monitor your code. Let's take a look at really what is happening inside Git. There are three areas where Git happens. This is the first area, this topmost level, where you have files that you see. And we call this working tree or working directory of I mean, both are equally good. So this is just files where you can make any kinds of changes that you want. And Git doesn't really care that much because it doesn't monitor anything in there. What Git cares about is this invisible folder, which we actually call a local repository. That's where things happen for Git. And inside that local repository, there is another thing. It's actually just one single file, which is called index. And we know it from Visual Studio Code as staging area. And this is what it actually is. And Git also calls it that way. When you read documentation, not plumbing documentation, but those porcelain documentation, then you can see that this is really called staging area. So what is the correlation between these three? What is happening when things change? Well, as I said, you can do things in the working tree. You can change content in there, but Git does not care. Only when you ask Git questions, like Git status, for example, then Git will go and try to see, what do I have in the working tree? What do I have in my local repository? And then it will update the index. And then it will present the contents of the index to you, actually not to you, but to VS Code, which will then translate that to those staging area or working tree file changes that you see. We will see just a little bit about it, but not too much. So, as I said, Git doesn't do anything automatically. It is never triggered. It is always only invoked. So what really happens during staging? I will just open a demo at this stage. So let's start with this one. I have this same working directory which I've presented just a moment ago. So there are three. We call them dirty files because they haven't been committed. And because Git status is run in the background, we can see this. So we can see that we have three dirty changes in here. And then, since I want to know what's happening inside the Git folder, I can see that there is not even this index file that I've mentioned, or no object files. This is just a freshly initialized repository, so everything is dirty. So let me actually just store these. Let me put them into staging area. So let me stage these files. What happens when I stage these files? So there are three files, as you can see. And I can see that now I have this index file. It's a binary file. You can read it. I don't recommend that you hack through that. There are ways how you can inspect its content that are less intrusive. But then let's take a look at this objects folder. We have two objects in there. So why two? What do you think? Well, don't try to answer. It's going to be difficult to moderate the discussion yet. So we have three files and two blobs. Well, that's easy. Again, I have this README file, and I have this games file, which has content, where's Waldo, and then I have rules for this game, where's Waldo, where I have written nothing else but just the title of the game so far. And these two files are exactly the same content. So Git doesn't need to hash them twice or store them twice. It knows that this is the same blob. So it is efficient. Good. So essentially, this is what we get. We get exact these two blobs. I'm just using first four letters of SHA because that's minimum that you can use with Git. Whenever referring to SHAs, you need to use, you can use the whole SHA, which is going to be 40 hexadecimal characters, but you can only use the first four. So we get these two. So what will happen? Here I have shown commands that have been executed. There is no git stage command. It doesn't exist. This is the command that has been executed to actually get these files into the staging area. So we actually had to tell Git that we intend to store these files when we next commit. And then let's take a look at what happens when we really commit this into the repository. So I will just take this and I will create a commit. I will just type a commit message, first commit, an amazing one, and I will commit that. And let's take a look. Now I have 5 objects. Wow, what do you know? So one of these 5 objects at least should be familiar. This is this one, commit. And most people have only known SHAs from commit because they think, yeah, Git attaches this SHA to commits, but that's all. Actually, Git attaches SHA to a lot more things than commits. It attaches SHA to absolutely everything. So let's take a look at what these 5 things really are. So when we take a look at our local or working tree, Git first translates that to number of subtrees. In this case, 2 subtrees, one for the root and then one for this rules folder. And then it also creates this commit object. And then we can see that this commit has its own SHA, every single tree has its own SHA, and every blob has its own SHA. And let me plumb a little bit more through this repository now that I have these objects. What I will do is I will just ask Git a little bit about these objects. I will just do git cat file, and then I will start with this familiar one. This is this 5264. We know it's where's Waldo, so yeah, I need to tell what I'm interested in. So I will say, just tell me the content, pretty print. So it will just print, this is the contents of this blob. And how do I know it's a blob? Simply by asking for the type. So type is blob. Good. Let's take a look at other ones. I know already from the slides that this A8 is another blob. So these other ones like F9, B4, F7, they are something else. So let me actually start with this B4. So what is this? Let me just, actually not B4, I will go with this 9F. So 9F, and then whatever the rest is, 3.8. And 9F, yeah. Oof. Okay, there we go. It's a commit. So good, I know that this is a commit object. And then let me pretty print this commit object to see what's inside. And now I see that inside I have a tree object, and I have some properties like who is the author, who is the committer, and when was this authored and committed. And I also see the commit message. Good. So I see that I have this tree called B4 something. So let me just cat file that. So I'll just say cat file B496, and then pretty print, type first. This is a tree object. And then when I pretty print, I can see that it contains 2 blobs and another tree, which I could, again, cat file to see, but it's a tree with another pointer inside. So what we see like this, Git sees with different eyes. To Git, this thing actually looks like this. It's a hierarchy of objects where at the highest level we have a commit, which has its own SHA. And this commit points to a single tree, which is the root of that commit. And that tree has a number of pointers to other objects in there, where, for example, in this case, we have 2 pointers to blobs and 1 pointer to a tree, and that tree points to exact same blob through another pointer name, which is this where's waldo.txt. So this is the contents of the commit. This is what happens inside. And as I said, Git hates duplication. Git actually wants to be as efficient as possible. So what Git will do is Git will always do this thing. When if it sees that there are 2 files with different names but exact same content, it will just use the same blob and just point to it from 2 different trees. You could have 1,000,000 copies of, let's say, app.json, all the same, in 1,000,000 folders. Git will only store one tree and 1 blob if it's all the same, just copies of the same. So Git is really efficient when it comes to that. So as you can see, Git is not that stupid after all. So we have seen that the index is a blueprint for the next commit. It defines what is it that we are going to commit. Commit operation creates a commit object which always points to a single tree, which is the root of that commit. Trees are catalogs of pointers to other blobs or trees. And Git hates duplication. Good. Now that we are going a little bit up, we've seen at the deepest level what Git is, and a little bit higher level. Let's go to this probably highest level that we see as users, that Git is a revision control system. So what does it mean to be a revision control system? That means that you need to have at least these 4 capabilities. You need to be able to manage changes of data over time. You need to be able to identify differences between different revisions. That's why it's revision control system. You need to be able to isolate changes that are happening. And you need to be able to integrate the changes that have happened. And Git satisfies all these. It just has its own terminology over that. So Git manages history of commits. It also is able to identify differences between these commits. It allows isolation through branches, and it also allows integration of these branches. So let's take a look at how this happens. Let me, again, go deep down into Git to see what is going on. So let's imagine I have this other commit. So I will go in here, and I will just add another game. I will just say Monopoly. I'm ready to define the rules for that game. It doesn't really matter, capital, lowercase, whatever. I will just now stage this and commit this as a second commit. And yeah, let's not go into Git folder to see what happened. Let's just take a look at this level. So first thing that we have is the new commit object, obviously. And this commit object obviously also points to a tree, because it has its own root of its own content that it stores. But it also points to a parent. So it is unbreakably connected to this parent. Again, SHA, for example, for blob, SHA is calculated from the contents of the blob. For trees, SHA is calculated from the list of those pointers inside the tree. And for commit, SHA is calculated from everything, from not just like from blobs and from trees. Essentially, what you get when you print a commit, that's what defines a commit. So SHA is calculated from that. And now you might ask a question like, why are these two different? Because it's the same root. Like, I have exact same files. I didn't change. So why did the SHA change? Well, it's easy, because in this case, I have these two which are exactly the same. So I didn't change one file, and I didn't change this tree that points to rules. But I did change games.txt. I've added something. So there is a new SHA for this new blob, and I need a new pointer. And since there is a new pointer, I also need to change the SHA of this tree. So this is how this works. Good. Then let me address some more common misconceptions about Git. A lot of people, because they see how Git behaves from Visual Studio Code or from DevOps or from GitHub or wherever, and it seems that Git stores deltas. And you think that Git tracks changes because that's what you see in Visual Studio Code. But this is actually wrong. Git does not do that. Git actually handles snapshots. It stores snapshots. It tracks content, not changes. And then you could say, well, it's potato, potato. Like, what difference does it have? Well, it has a lot of difference. So let's take a look at this picture. I have quite a little bit of mess. I have two commits. But the first commit is this. And this is the snapshot at the moment of committing. And then I have the second commit, which is the snapshot of my working tree at that moment. And if I add another commit with some more files and changing files around, maybe I reuse some existing files, maybe add some more new files. But this is going to be a snapshot at that moment of my working tree at that time. And this is what Git stores. Essentially, every commit is a snapshot. It tells you exactly what your working tree looked at that exact point in time. That's what Git stores. So you could say, well, that's not true. I've seen this. Like, I've seen these everywhere in GitLens, in GitGraph, in DevOps, in GitHub. Wherever you go, you always see this. Yes, that is true. But that's not because Git does that. Git does not track changes. It's us who track changes. You know, humans are really, really bad at handling snapshots. Just watch this on YouTube in a week or two, and you will see that you are incapable of handling 60 snapshots per second that are happening in front of your eyes. But what you do perceive is a change. And we are good at handling change. So Git tools present that change to us, not because Git stores it, but because we want it that way. So it's always Git tools that translates these snapshots into changes so that we can easier understand and follow them. So all of Git tools do that. There are very few tools I've seen that actually present you the contents as they are. That would be unmanageable. It would be very difficult for you to see what exactly happened. So how does Git do that? Well, it calls this, again, a method or a command called git diff. Git diff works out the differences between two snapshots. And it also takes a massive advantage of SHA-1, again, another optimization. And whenever you want to know what changed, Git really needs to calculate it again. Every single time you ask for it, you get new calculation. And most often it's the same result, but you can tweak this command, at least when you're running it from the command prompt. So let's take a look at how git diff actually works. Let's take a look at this simple snapshot of a repository. We have first commit and second commit. For you, it's very difficult to spot the differences by just looking at that. They look quite the same. It's just like those two spot the differences, children pictures. So what does Git do? First, it goes to the root, and then it checks the SHA to see if the SHA changed. If the root SHA didn't change, then it doesn't have to check anything else, because then everything else inside is exactly the same. Here, it sees that, okay, this is different, so it will mark that for further deeper inspection. Let's go to the next tree. Next tree has exactly the same SHA. And then Git simply decides, okay, I don't need to look into it. It can contain 70 million files. Git, simply by checking the SHA, knows that, yes, that's the same content in there. So I don't need to inspect file by file. So it skips. It goes to the next one. So yeah, SHA is different, also name is different. So I really need to look into this very deep. Good. So now it knows that it has, out of 3 trees, it has 2 trees to check. So it goes back to the first tree and then compares this. And it says, okay, object ID config, same SHA, nothing changed, I can just go on. And then it sees app.json, different SHA, so this is a modified file. Now, if we want to see the contents of the modification, we can do that as well. Git diff can tell that as well. But let's say we are doing it on a higher level, just on a tree level. So we know this is a modified file inside of this second commit. Then Git stops processing this tree because it has done it, and then it moves to the next tree it has. Here we have the same SHA, but different name. So what happened? Well, a rename operation. You just change the name of a file, or move the file, in this case, to a different folder, but you didn't change the contents. The contents remain the same. So Git knows that this was a rename operation. And then we take a look at the next one. Okay, this is different SHA. It doesn't have anything like that. So it says, okay, this is a new file. New SHA, new name. This is a different file. So it records this as an addition. And here it sees different SHA, something that doesn't even exist on the right side, and name that doesn't exist. So it knows, yeah, this is probably a deleted file. And this probably is the keyword. Git never knows for a fact. What git diff does is a very educated guesswork. In most situations, it is pretty smart. It can detect everything that happened exactly as you want it to be recorded, but sometimes it will give you wrong answers. That's just because you can do things like, for example, you can take the same file, you can rename it, and change the content at the same time. And Git might not be able to tell you that this was actually a rename plus change content. It will just tell you, yeah, you deleted that file, created this new file, and then you lose track of that. So Git is not all-powerful because it doesn't care about changes. It simply cares about snapshots, and it will do its best effort to present those snapshots as a set of differences to you. So in this example here, we now have a change set, as some people would call it, which contains 3 or actually 4 changes, 1 modification, 1 rename, 1 addition, and 1 deletion. But that's not what Git sees. That's what just it presents to us, because we are better with that. Good. Now let's talk about branches a little bit. Branches are used to isolate work between developers. So when I work and when you work, we usually do not want to trample over each other's feet, so we simply typically start a new branch. So let's not talk about branching models and best practices and all. Let's just talk technically about branches. So a branch simply isolates your work from your colleagues' works. And in Git, branches are also pretty smart, pretty efficient. So what is a branch? Let's take a look. I will just open another demo. And let's take a look at the contents of the Git folder. We know that Git stores stuff in here. And some of that stuff, like index, that's binary. And we also know that these objects are some zipped objects. You could really unzip them to see what is in there, and then see that they are exactly what I described. But where does it keep branches? Is it also objects? Like you could assume, especially if you come from TFS, that when you create a new branch, it actually duplicates everything somewhere else so that you can work on an isolated set of changes. That's not what Git does. So branches in Git are stored here in refs. Git also refers to branches as references or heads as well. We will see a little bit more about that. So refs. And then inside refs, we have heads. And then we have this master head. So when I click this master, it tells me this. So what is this? A SHA. Good. What does this SHA point to? Well, I can figure that out because I know how to. So I go to my terminal, I say git cat file, and then I say pretty print, or actually give me a type of that. And then I type the SHA 006cc or just C, and then it tells me this is a commit. So I see that I have a file which is named as my branch, which contains simply the ID of a commit. And that's the branch. That's all there is to branches in Git. If I, for example, do this, like I create a new branch, so let me do that. I will just go in here and I will type git branch feature 01. And what happened? I just have another file here with exactly the same contents as master because they are currently pointing to the same commit. If I click git graph, I can see that. So both of these branches are here. Good. So what happens when you commit? Well, Git simply advances. It changes the contents. So let's take a look. I'm now inside. I'm going to check out into git checkout feature 01. I'm intentionally using commands so that you can see that this is what is happening when you click around Visual Studio Code. I'm not saying that you should do that. Absolutely no benefit of that. I just want to tell you that this is what's going on. This is under the hood session. So that's why. So I'm now in the feature branch, and let me do a modification. I will just go in here and change this to version 0.1, and I'm going to stage this and then update version and commit that. So let's take a look at feature branch. So I commit this, and this file changes. It now points to the SHA of this commit, and that's the branch. So if I keep adding commits like this, Git will simply update this file. That's all there is to branches. And then let's imagine that master has advanced, like somebody has merged their work into that, and then you are ready to merge your work into that. What happens? You create a merge commit, and then you delete this branch. So you have simply deleted that file. Git doesn't need that file anymore. We will talk a little bit more about deleting branches. So in Git, branch is nothing more but a name for a commit. Nothing more than that. It's just a small file with the only contents of that file being SHA of the commit that that branch currently points to. So that's a branch. So how does Git know which branch is current? Well, apart from having these branches in here, inside of heads, it also has this file called head. And let's take a look. Head says refs heads feature 01. So it's another pointer. So let me check out to master. So git checkout master. This is what happens. So I've changed branch. While it is somewhat safe to, I could go in here, create a new file called whatever, and then put the SHA in there, it would work. And I could delete it, it will also work. This is not recommended. Don't just, a few more things happen when you check out into branch, not just like change of this in here. But yeah, let's not go into that. You should generally not be hacking in this folder. Even if you know what is going on, it's not recommended. So, but that's all there is to current branch. So when you add a commit, then, like for example, now we are in the feature branch and we check out the feature branch. The only thing that changes is contents of this head file. Apart from, yeah, Git synchronizes the index, Git synchronizes the working tree as well. That's why I'm saying, like, do not touch that file manually. So, but just contents of this file have changed, and now it points to something else. And then you add a commit. So you commit something. What does Git do? First thing that it does, it looks into head. And then it sees, okay, head points to feature 1. And then it simply advances feature 1 to point to that new commit. And that's all that happens. So that's how Git knows which branch is current. So let's talk a little bit about the concept of detached head. Maybe you've heard of that. Can I see? Did somebody hear of detached head? Have you ever seen this ugly looking message, you are now in detached head mode, blah, blah, something scary? Yeah. So it's not scary at all. I mean, Git could completely work in this detached head mode. So what is detached head? As you could imagine, it is simply when this head points to something other than another reference or another head or another branch file, when it simply points directly to a commit. So yeah, I can do that. So I will just go to this detached head demo, and let's take a look at the history that I have. So in here I have 3 commits. So I will just select this one. Okay, it's 80 something, 809D, whatever. So let's open this head file, and let me just, through the terminal, say git checkout, and then I will just move this file around. And I'm interested in this number in the SHA, so I'm checking out to 80E9, and then I get this checkout, yeah, typo, checkout, and then what happens is that head file changes, it points directly to a SHA. I get this message here that says you are in the detached head mode, blah, blah, whatever, and then I'm working in this mode. So this mode is not scary. This is nothing to be afraid of. This is a typical thing. It's typically something that you could do for debugging. Like, for example, you know that something used to work over the past 17 commits you did, but you're not sure exactly where. You can just detach head into each of them and figure out, okay, this is where I broke it. There is even a Git tool for that, Git bisect, that can do it automatically. Like, it just keeps checking out until it figures out, okay, this is the branch, or sorry, this is the commit that broke whatever you broke. You need some unit tests for that, but yeah, it can do that for you. So that's detached head. That's the mode, and that's what it does. So what happens when you commit when you are in the detached head mode? Because you can do that. Exact same stuff happens. Git first looks into the head file. It sees, okay, I'm in detached head mode. So I simply need to update the contents with the SHA of this new commit, and I'm there. And then if you want, you can create a branch from that point, or you could just exit the detached head mode, just decide, well, I don't need this commit at all, so you move out of that. So this is detached head. And now let's talk about deleting a branch. What happens when you delete a branch? We have seen already that when you delete a branch, simply this file disappears. So that is easy, because in this case, we delete a branch that points to a commit, but that commit is a part of our history, of our main line. We have master, which has 2 parents, because that's a merge commit, and now we see that, yeah, this commit to which this branch pointed is inside the history, so it's safe to delete. But what happens if this is the case? So you didn't merge the branch, and you decide to delete. Well, okay, let me demonstrate quickly. I'm going to go into this demo where I have exactly this situation. I have master, which is advanced 2 commits ahead of my branch. So I want to delete this feature branch. So let me do that. I will just do branch, git branch -d stands for delete, and then branch name feature 01. And then Git will complain. It will tell me, no, wait. If you delete this, what happens with these 2 commits? Take a look. They are not a part of the history. So Git is smart enough to tell me, wait, I want you to consider that you are really sure that what you are doing is correct. And the same will happen here if I just do delete branch and then choose feature 1. Yeah, I get an error message which tells me the branch feature 1 is not fully merged, to delete anyway. And if I say yes, delete branch, what will happen is this, that I should use the capital D in here. And when I do this, let's take a look, gone. So commits are gone. So branch is gone, and these commits are gone. So I don't see them anymore in my history. Well, the same thing would happen, for example, if I'm in the detached head mode, and I've done one commit to see, okay, what would happen if I've identified where I did something wrong. Let me try to quickly fix it by doing a commit there to see if this would be better. And then I realize, nah, really no. So I'm just going to abandon this commit. So you just exit out, you check out into your branch. Well, this commit is gone. So this is the situation, like you have those dangling commits. So these commits are not deleted. We call them dangling. That's the official term. They are still in the database. They are not deleted. They could get deleted eventually, but Git is going to preserve them for you for a little while. So let's take a look about recovering commits. Git never loses anything. If you ever perceive that you have lost something, that's just your perception. Well, this is at least not immediately true. So Git might delete stuff for you, but not immediately, never immediately. You have ample grace period, as you will see. And also, you can recover from all situations, unless, of course, you're hacking to this Git folder, which I said, do not do that at home. So let's take a look a little bit about how can we recover lost commits. There is this thing in Git called reference log. And again, it's not the same thing as log. It's not potato, potato. It's a completely different thing. Git log is what commands, like what tools execute when they present the graph to you. So you will see the history of commits on your main line or whatever your current branch is. That's Git log. Git ref log is reference log. It keeps track of changes to heads, all heads, which is all branches. So whenever a tip of the branch changes, which is typically when you commit something, reflog will keep a track of that. So let's take a look at this situation here. I'm now in this repository where I've just deleted the branch. And I've seen 2 commits in there, but they're not in here. I only have these 4, so I will do git reflog. And I get this list. This is not history. This is history of changes to tips of branches. I can see here how I was switching between branches, which branch to what branch, at what time. So this is the reflog. There are deeper ways to look into that. It is a plumbing command, but it can be even more plumbing than it is. So what I can see here is that I have some SHAs, which I don't see in this list. Like, for example, this one. So this was a tip of my head, and this was the tip of my head at some point in the past, but I don't have these commits in here. So let's take a look at, now I know that I can detach my head into them. So I do git checkout, and then this, for example, 6695. And look at that. I'm somewhere checked out into a commit directly, which was lost, but it isn't lost because it's never lost. Never is a long time, so let's not talk never. But these are the things that you can do. So nothing is really ever lost in Git. We have another way of identifying things. So let me now check out back to master. So git checkout master. And again, this was detached head state. So this commit is again lost, kind of, but it's not. So there is another command. It's git, it's not it's file system check, fsck, and then you do this lost-found. And it will tell you that you have 1 dangling commit. But why 1 when I know that there are 2? Like, I've seen that there have been 2, like reflog has shown 2. Well, because the only really dangling commit is that first commit. The other one is referenced by that one, so it's not really lost. If we recover this one will be automatically recovered because it's referenced by that one. So reflog will give you one view over what are your lost commits, and file system check lost and found will give you a different view of that, but both of them will help you identify where did this content go. So this is a little bit about how you recover. So steps to recover. Actually, let me just say a little bit about garbage collector. Yes, Git will clean up for you, but not just like that. So any dangling commits are left for a minimum of 14 days. But if they were ever tip of the head commits, like they were ever like commits to which a branch has pointed, they will be kept for 90 days. That's the duration for which Git keeps ref logs. And after 90 days, Git will clean up ref logs. And when it cleans up ref logs, these commits are up for grabs. They will be garbage collected. But until those 90 days have passed, you still have a chance to get them back. Git will automatically run garbage collector. I mean, you can call it directly if you want, but Git will do it for you every time you do fetch, when you do merge, when you do rebase. And there are some those, plumbing commands which will also do it for you, but they are not that relevant because you are most likely never going to call them, or even your tools. And Git also allows us to rewrite history. So Git allows us some ways of manipulating this stuff that has happened in the past. We can, for example, reset commits, we can amend commits, we can interactively rebase. We will talk about that as well. But what is important to understand, this is never modifying history. You cannot do that with Git. You can only ever create alternate histories. One of the properties of every commit object is the timestamp. So there is no chance that by modifying history you would ever end up having same SHA, because timestamp has changed and timestamp is hashed. So this is always going to just be alternate history, even though you may perceive it as a real history. So let's take a look at resetting. You could think of resetting as git undo. So what does it do? It actually moves the head pointer backwards. And it is useful, for example, when you commit something and say, no, I shouldn't have, then you fix it. Or maybe you want to correct some commits, so you undo and then correct and then commit again. Or maybe you want to remove some commits from history. Then you just reset, do some changes, and then you get rid of some commits that you didn't want to have. Or maybe you want to squash. Like you have 5 commits, you undo all 5, and then just squash them together again into 1 commit. We will see about all of these shortly. But let's take a look at this git reset command. So let's imagine that we have a tree that looks like this. So we have this branch that points to this tip at the top, like this 00A0 commit. And then this is my head, and then I can do something like git reset and then SHA. And I tell Git to look for that SHA in the history, and when it finds it, it will actually move my, not head, but my branch, because that's where I currently am, and this branch will now point to this SHA. But this is also, there is an easier way. So instead of just writing SHA, you can just do it in steps, like git reset head ~1. So what does this stand for? Head stands for current branch. In theory, you could just do that with any branch, but I don't see the point. And ~1 means 1 commit in the straight line, taking into account the first parent. Like this is strictly speaking what it does. There are other ways to traverse the branch or the history, but this is the most common one. Like just undo the last commit. And then it does. What happens then is that you just get 1 dangling commit, and something else happens as well. So let's take a look. I will just open a demo here, and I will demonstrate. Okay. This reset head tree. So I have this git graph. I have these 3 commits. Every commit has added 1 file. So this has an added file. First, second, third. And I will open my working tree here, and then I will just do git reset head ~3 and press that. And what happens is that Git has actually put these into my working tree. So whenever you do this, whenever you do git reset, it moves the current branch. And then, of course, it dangles these commits until you maybe perhaps just move the head again back to the same position, and takes the contents and puts them into the working tree. And now they are there. And you could also do it like this. You could say git reset head ~3 whatever -- soft. This will put them into staging area. Or you could just say hard. Of course, it will just get rid of them. So they will just stay dangling. And then there is a way to directly modify commits. So, for example, you could you realize, okay, I made a typo in my commit message. I want to correct that, so you can amend a commit. Or you realize, oh, there was this file which wasn't staged. I want to make that part of my commit as well, so you do that. Or modify some properties, like I want to fake Waldo. I say like, okay, Waldo committed this just because, yeah, there's some shit in there and I don't want anybody to know that it was me. So yeah, Waldo, and fine, now commit amended, different author, yeah. It never actually changes the last commit. Let's take a look. I'm going to amend a little bit. So I will say that I have this amend demo, where I already have a commit in the database. So I have committed this. And now I have some more files, but I realize, I've forgotten about this file. This should have gone there. And then I just say commit amend. And then it asks me, what is your commit message, please? And I say, well, I'm fine with this, so I will close this. And then what happens is I get this first commit with second file in there. And then I say, yeah, fine, I also want this third in there. And I will just do this. I will just say first commit different message. So now I've specified the message, so it will not ask me again. So I do git staged amend, and I can take a look, and I have this message and different content. But this has not changed the original commit. It has added more commits to the database and just kept the other ones dangling. So if I had this situation, and then I decided to amend, and then I decided to amend again, I simply get new commits and the other ones are dangling. Maybe I will want to recover them, maybe I will not want to recover them, and they will be garbage collected eventually. So this is simple history modification. There are other ways. What is important to know is that all of these things are only safe before you push, because they are destructive. They actually modify what your history looks like. So when your history is up there on the remote, you cannot do these things anymore. They are just not compatible. Git will never allow you to move your tip of the head on the remote backwards. Well, I mean, there are ways, of course, but they are all hacking and recovering from people who do something. And I will show you what that something is with a big caveat. So any destructive changes are automatically prevented by Git. And then you say, okay, but this is my branch. I know what I'm doing. So yeah, you can do git push force. And then git push force will simply send whatever contents you have to send. If the SHAs are already there, it will not send the SHAs, but it will update the tips of the branches on the remote without checking. So it will just, if you push your branch, let's say feature 1, and you have reset 3 commits, it will simply update the tip of the branch in there without checking, is it safe to do so? So it could feel that you have solved your problem, but it might not be the case. So I'm not saying that you should ever do that. Yes, if it's only your branch and if you know exactly what you're doing, this could be safe. I mean, I have been doing that, I will be doing that, but I'm saying be careful with that. Don't just routinely do this, so it's better that you do not do destructive changes in the first place. So a little bit about this revision control. Some takeaways. First, branches are just pointers. They are not adding overhead to your Git system. Git never loses anything, at least not for a while. Lost commits can be recovered, at least for a while. And you can freely rewrite history before pushing. So you can manipulate what you're going to push. That's why it's there. So you are working like what I'm often doing. Like I do a lot of commits, this, that, and then before I'm about to push, I just look at that and clean up if there is a mess that I don't want to be there. Like why do I need in my history some fumbling between some files where that's not relevant? But this is something that you can just do before pushing. Like after you've pushed, whatever is there, let it stay. And let's talk a little bit about integrating changes. So what is integrating changes? What is integration? And actually continuous integration is about this kind of integration. This is, well, colloquially we call it merging. I've merged my branch. My branch is merged. So we just say merge. But merge is just one of many ways how you can integrate changes between different branches. So what really is integrating? Well, you have, let's say, a mainline branch, whatever you want to call it, and then you have some other branch which contains some commits that somehow need to end up in there. That's why I'm not showing those, lines, what is the parent, whatever. And you simply want these commits to be part of those commits. So that's integrating branches. And then let's take a look at the ways how we can integrate branches. The first way, the most common, the most obvious way, and also probably the most intuitive way, is merge. This is what Git will do unless you tell it to do something else. So what is merge? Imagine that you started from here, this is master branch, and then you branch out into a topic branch, and then you advance by 2 commits. And of course, you know master advanced because other people have been committing their stuff and merging their stuff. So you have some more commits in there that you don't have in topic branch. So what you do, when you merge, you in fact create 1 commit with 2 parents. So it points to 2 different ends. And it essentially combines 2 histories together into 1. And from that point on, both of these parallel histories are 1 history. That's the point of integration. It combines histories. Good. That's the merge. It's, as I said, like the most intuitive one, really easy one to follow. And these are the commands. When you merge, you typically delete the branch. And this is the best practice. 2 things that you should never do. Once you have merged your branch, you do not continue from the old branch. You can do that safely only if you have first merged your branch into master using fast forward. But I mean, just delete and create another branch with the same name for all I care. But never continue developing from the commit that was the parent of the merge commit. That's how you get repeated conflicts and issues downstream. And in other workflows, other than merge workflows, it can be especially dangerous. Another thing that you should not do with these topic branches is branch off them, because that's another recipe for disaster. We can see about that. Let's talk about another way of integrating changes. This is fast forward. Have you heard of fast forward? Yeah. Okay. Do all of you who put your hand up know exactly what fast forward is? Well, now there are fewer hands up. So what is fast forward? I mean, we often hear that or see that, or Git was able to fast forward. What is this? I don't have a clue. But let's take a look. It's nothing special. So let's imagine that you have added 2 commits to your branch. And in the meantime, nobody has added nothing to your mainline. So what can you do? I mean, there is no need for a merge commit. There is only 1 straight line of history. So you fast forward master branch to simply point to that last commit. That's fast forward. Because there are preconditions under which Git can do that. That's that there is only 1 single straight line, and you are on that line already. So you just fast forward this, and then there is no need for an extra commit. Extremely simple. And this is the cleanest situation. So you actually want those situations. They are your friend. Whenever Git can fast forward, you should be happiest, because there are no conflicts with fast forwards. This is just, just advancing, because everything that is happening on the main line is already in your branch. That's fast forward. Very, very simple. And then there is this funny one. Okay, I'm showing commands. When you fast forward, you also typically just delete that branch because you don't need it. There is this interesting one. It again depends on your branching model. So some branching models want this. Like for example, Git flow. I will not go into qualifying like is it good or bad. If it works for you, that's fine. But Git flow actually wants this to happen. And DevOps, for example, allows you to configure your pull requests so that they actually demand this. So even though it's possible to fast forward, like in this situation, you actually want to do this. Why? Because you want to see that another branch was integrated at this point into this mainline branch. So you get a commit which contains no information whatsoever except parents, because, yeah, like it just integrates histories. Well, it does contain a lot of information because it does contain tree and everything. But it is just, it contains exact same content as this fast forward, just another SHA, because, yes, we wanted another timestamp and another whatever, just because we wanted to see that it happened. It is legitimate, I mean, especially for some branching models. And that's what merge with no fast forward policy really means. So even if it was possible to fast forward, you decide not to. You just decide to create a merge commit because you want to see that in your history. And of course, you would again delete your topic branch because that's the best practice. And now we get to the really interesting one, rebase, my favorite. So have you heard of Git rebase? Do you know that it's dangerous? Yeah, of course, it's an ugly, ugly, scary beast. Don't play with it. So what is this rebase? What does it do? So let's take a look at this typical situation. Like you do some development, your colleagues do some development, and then you're ready to merge. And then instead of merging, like creating a new commit on top, you go back to the base. Your base is that point from which you branched off this tree. And then you simply cut off that branch at that point, and then you take that branch and put it on top of the tree. That's rebase. I mean, that's what at least it feels that is going on. But if you have been paying any attention whatsoever to anything I've said, especially in the beginning of this session, you know that this cannot happen. Because the commit has just gotten a new parent, and it cannot happen. Like, that cannot be, because commit always stays attached to the same parent. So what really did happen? I mean, logically speaking, that's what happened. But speaking about storage, on Git level, this is what happened. You had this situation to start with, and now I'm adding numbers or identifiers A, B, C, D, so that we can see what is going on. So we have these C and D commits on my feature branch, and I decide to rebase. Git cannot cut that branch off and attach it on top. What it can do is it can replay that branch. So it simply does a git diff to figure out what was the difference, and it replaces it, and then another, and replace that on top. And now I get two copies of commits. So C prime and D prime, which make it look as if I have just worked on top of that point so that I could possibly fast forward later. That is what typically happens when you do this. You simply fast forward the master branch and get rid of the topic, and then it leaves these two dangling commits. You don't need them anymore. They are merged. You should just forget about them. So that's what rebase does. And now let's address why people perceive that this is dangerous. So let's roll back a little bit, and let's talk a little bit about merging. Imagine that you have this. You have master and topic. And the correct workflow is that you are merging topic into master. So you do git checkout master, then git merge topic, and then you git delete topic if you want or not. But exact same results, just with inverted parents, would happen if you do git checkout topic and then git merge master. You get exact same histories, and it doesn't really matter from which angle you did that. Once that you fast forward your master or delete your topic, it's exactly the same. Just, left and right side are flipped. Semantically speaking, it's not strictly the same, but content-wise, it's exactly the same. So when you do merge, no problem. I can do it from this direction or that direction. I'm your man. I know what I'm doing. It's fine. But with rebase, that's not the same thing. So imagine that this is the clean thing where we had those C and D commits, which are now C prime and D prime, and I don't care about C and D anymore. They are dangling. I don't care about them. I have integrated my work into my main line. So that was the correct way of doing rebase. But imagine that instead of me doing git checkout topic and then git rebase master, I do git checkout master and then git rebase topic. What did I just do? I killed my entire history and created an alternate history. And then I've, my master in my local repository now contains a history which is nowhere to be seen in remote. I cannot push that. And of course, yes, this is dangerous. So, and if you have this situation, then you are, screwed. So that is why it is dangerous. Of course it is dangerous, because that's not the same thing. It's just like the chainsaw, Is it dangerous? Yes, I absolutely agree. Totally dangerous tool. I wouldn't myself want to handle it. But if you're a master of that tool, you know that this is how you hold it. Fine. But if you want to do it like this, of course, it's just going to cut off your fingers. So completely up to you. That's what rebase is, and that's why it's dangerous. It's actually just powerful, and that's all. Some flows, like trunk-based development, where committing to master is totally expected from you to do, this is the typical thing you do. You just rebase all the time. Just remember, never rebase from master onto something, but from something onto master. And that's it. Let's talk about squash. What is squash? Again, I have these A and B commits. I don't need them as A and B because it's too much information for my history. So what I can do is I can squash them into one. So I have A, B prime, which is essentially replay of both commits as one commit. and contents of my tree are going to be exactly the same as over there. Just remember, one thing that I did not address here is that all of these operations can involve a conflict. If your contents conflict with the contents of the branch onto which you're rebasing, or into which you're merging, or into which you're squashing, you will always have to handle them anyway. So I'm intentionally not mentioning that not to complicate things. It is simple because I just want to explain what those different ways of integrating really do. But remember, conflicts can happen. Let's just not address them here. So this is squash. You simply just take two commits, put them together, put them on top, and that's it. And then we have another one, which is interactive rebase. So with interactive rebase, it is very similar to rebase, except that we want to take full control over the replay process. So depending on which tool you use, when you start interactive rebase, your tool will present you with some choices. So if you, like for example, this is Git Lens, an amazing extension for Git for Visual Studio Code that I really recommend. It will give you this nice graphical overview. If you don't have Git Lens, it will just be Visual Studio opening that file that you have seen. Like when I was committing, it put this commit message file with some comments and some instructions in there. It will do the same for this, for interactive rebase. So what does interactive rebase allow me to do? Well, you say that you want to rebase onto some specific commit or onto some specific branch. And then it presents you with the list of all commits that would be replayed. And then it allows you to do changes to it. Like, you can decide to edit a specific commit, or you decide to drop a specific commit, or you decide to modify the message, or you decide to squash some commits together. Like you get the full control over what is going to happen. So for example, in this case, I have one edit, so it will replay this bottom commit, and then it will stop and allow me to change the contents of that other commit which is being replayed. So very, very powerful tool, really. Even more powerful than that, chainsaw, but also very, very useful. So with Git interactive rebase, you typically end up with scenarios like this. Like you take some contents of your branch, put them onto another branch, and then you move on. And then, of course, you would just fast forward your master, and then you would get rid of your topic branch. So, and then I have one more, which is cherry picking. So I believe you have heard of cherry picking. Cherry picking is also a way of integrating changes from one history into another history. So what exactly cherry picking does? Well, first of all, you are in the branch into which you want to cherry pick from another branch. And then you say, I want commit A from here. And then it advances your head immediately. And then you say, I want commit C from here. And it again replaces that. You don't take those commits, you replay them. So that's why we have A prime and C prime in this case. That's because we have simply just decided to replay them. We cannot just change the parents. So those are the ways how you can really integrate with different branches in Git. And that was all that I prepared. So we have 15 minutes left for QA. I thought that would be just about enough. If you think not, then we can stay longer, but yeah, I'm not going to commit to that. So, thank you for your attention first. Yeah. Good morning, Waldo. Okay. So, which Git pains do you have? Yeah, let me start here.
We often use cherry picking,
Mm-hmm.
but also a lot of times, about 50% of the time, you see invalid object.
Just sorry. Do we have a microphone for audience when they're asking questions? We do. So let's just wait until it arrives. I don't see it here, so yeah. Why are you Git pulling out? Okay, there is no microphone, so I will just repeat the question.
It
Ah,
is.
there is. Yeah.
You have to throw everything.
Yes, I know that. I'll try to not kill anybody because once I almost did. So,
Hello?
does it work?
I don't know.
Okay.
Okay. Right, so we often use cherry picking. I don't know why. Somebody told us that. But in 50% of the time, I get invalid object when I try to cherry pick a schwa.
What kind of object do you get?
An invalid object.
Invalid object.
Yeah. I
Okay.
have no clue why it is.
Well, I really cannot tell you. What are you using to cherry pick? Are you cherry picking
With command line.
online? So you are in DevOps and then you cherry.
In command line, I just have it in the VS Code and then do git cherry pick schwa, which I get from DevOps.
I don't know, but I could say like if you cherry pick a merge commit, I would imagine that you could get some mess.
Yeah.
That's not what you should do. You should not cherry pick merge commits.
Okay.
They are not intended to be cherry picked.
And sometimes it works, sometimes it doesn't.
No, that can depend, I guess, but that's not a good practice. That's the only situation where I can get that you could consistently expect problems. Because merge commits are not, they don't have, I mean, they do have content themselves, but it is just content that they are essentially just conflict resolutions when you look at the Git diff perspective. But you don't want to cherry pick from them because it's very difficult for Git to determine what exactly changed because it has two histories. It can have three. I mean, you could. It's,
okay.
I'm not saying it easily can, but never cherry pick from merge commits. Cherry pick from commits, other commits like normal commits, like those inline commits. Yeah. I can imagine that could be the problem, but without seeing the exact message, like the exact scenario, I cannot really.
Then doing is going into the pull request and taking the individual commits. And then, but then I need to replay all of those commits instead of doing one.
Well, then you can do interactive rebase if you have more cherry picks to do. Like instead of just doing one by one, you do interactive rebase and you just say this, not this, and
we'll call you later.
That's okay. Yeah, I need to give shirts out. So yeah. I have 3 shirts. By the way. Let me see. Let me hear. Clap your hands if you're using Object ID Ninja. Okay, good. Do you want a sticker for your laptop? Okay, then come after the session here. I will be giving stickers out. So, yep. And there was a question. Sorry, there was a question over there. Yes, exactly. So try to survive. Yep. Okay. And let me hear the question and then I'll decide if it merits a shirt.
I try. When we start to use Git, for example, also the merge the CAL code in TXT format, for example, but also in Business Central, we try to use this approach. We create in a single repository 3 branch that you always open. Not delete it anyway. And we try to use the 3 branch level, developer, test, and production, for example. Okay. But we met difficult because in several cases we have to resolve more conflict because we are 6, 7 developer that we try to attach same commit in the same time in the single branch. Now I understand why is this the wrong way, but I'm curious
an
to
excellent
know
question. An excellent question.
Yeah.
So absolutely, you deserve the shirt.
Okay.
And let me address this question now. So. There are many different branching models. What you have described is a branching model. I'll take the mic. A branching model describes how you should create branches. When should you create a branch? When should you delete a branch? When you should integrate the branch? And how you should do all that. It also describes into which branches you can commit or cannot commit. And different branching models do different things and require you to do different things. But not all branching models are equally good for everything. So I understand that a lot of people are struggling with finding the best branching model. And let me help everybody who is still struggling. The best branching model out there is the trunk-based development. There is a website called trunkbaseddevelopment.com with no dashes, no nothing, just trunk-based development. Read it. I honestly recommend. Like for me, this was an eye-opener. In that branching model, you have one branch called master or main or whatever you want, or trunk, it doesn't really matter. And everybody locally works in that same branch. And then when you do, you either, if you use a workflow which requires pull requests, then you just create a very short-lived branch to create a pull request, but otherwise you just push to master. And if it looks scary, like you say, like, what is this guy talking about? Well, let me just tell you this. Google has 3 repositories for everything they do. One is for Android, one is for Chrome, and this covers for 5% of what they do. Other 95 is, Google Docs, Google Maps, Google Search, etc. 80,000 people commit straight to master every day there. And that's why they are efficient. That's the most efficient model. Like no test branch, you can do them, but it's so much easier if you don't. Like your pipelines don't require an extra branch just to be able to run a pipeline. You don't need a branch for that, but you will have extra work to maintain that branch and to resolve conflicts on that branch. And the more branches you have in parallel, like those perpetual branches, the more work you will have to solve the problems that you wouldn't have if you didn't have them in the first place. And then, if you use rebase workflow, I did not show conflicts, but conflict resolution is much different between rebase and merge. Like a lot of people hate rebase because let's say you have 15 commits and there are 20 commits on the master and you now need to rebase. And then, bam, conflict. So you solve the conflict, continue, bam, conflict. You solve the conflict, bam, third conflict, fourth conflict, fifth conflict. Yes, that's how rebase works. It will conflict out on commit level, whereas merge will conflict out on the merge level. So, but that's why I prefer rebase. Yes, maybe I have more work, but this is really focused and I really know exactly what I'm doing. I prefer having like one small conflict per commit and then I resolve it rather than having 75 conflicts across 300 files and then I need to spend like 3 hours merging. So rebase is cleaner in that way. And then it gives you this much easier history to handle. So I really recommend, like, read about trunk-based development. Good companies do that. Microsoft does that. So talk to them. Like, ask them, how do you branch? They don't. Well, they do, but not like they're not so branch happy like the rest of us are. Yes, a question.
Thank you.
And a possible shirt.
Of course. Many times when I try to, it's not maybe Git, but after the merge and putting everything into DevOps, I get sometimes error, multiple merge branch detected. I have no idea why.
Can you please repeat? Like, what exactly do you do?
It's just a pull request to the test branch or master branch. It sometimes happens when a lot of developers working in the same branch, and I think there is some issue with some commits.
Yeah. Well, the only way to work in the same branch is rebase workflow. You cannot work in the same branch without rebase workflow. Otherwise, you will just have a mess all the time.
Always merge everything before.
But don't merge, rebase.
Rebase.
Yes. You cannot share a branch without doing rebase. I mean, you can, of course. Just if you want to do a lot more.
Different branches. Every developer has his own branch, but then we have to merge it into the one.
Yes. So you will get conflicts probably all the time because, like, if let's say 5 of us are working all on the same object and touch the same place in that, the first one that gets merged is happiest because, yeah, no conflict. But the next one will get a conflict and we'll have to resolve it.
Okay, I have no issue with the conflicts because I can resolve that. But then I have some kind of issue in the DevOps, which is this multiple branch base detected.
Well, then I would say that probably your DevOps is set up incorrectly. Like maybe you have too many branches to handle there. I would really need to know more about your branching model. But I mean, everybody can just figure out, like, every time you hear a question with problems, there are always multiple parallel branches involved. There is like not that many problems when there is just one. So I would really recommend, like, everybody who experiences merge issues or workflow issues when there are multiple branches, like I've seen people having, like, maintaining, I don't know, Q&A branch, test branch, pre-production branch, production branch, development branch, master branch. Nobody has a clue what they are. And maintaining all that, just what amount of work, unnecessarily. So, I mean, if it works for you, who am I to tell you not to do that? I'm just trying to tell you, look into how other people do things. Like, I think that, you know, Git is 17 years old, SCM is, you know, like probably 40, 50 years old, continuous integration is almost 23 years old, 33 years old this year. I mean, let's not reinvent wheels. Let's take a look at how professionals do that, like how Facebook does it, how Google does it, how Microsoft does it, how Twitter does it. They all have one branch. And then, yes, you can have release flow, for example, what Microsoft does. Then you just have a release branch, which is short-lived or mid-term lived, which you maintain to maintain a specific release. But it doesn't quite work with kinds of products that we develop. If you develop an offering, let's say something on SaaS, where customers can come to your website and then obtain a business central that you control and that you maintain, like Microsoft maintains their SaaS, then release flow is amazing. Like you have trunk, and you have release branches for each release, which you support for a while, cherry pick from master, something that needs to go in there, and then at some point it reaches the end of support, and then you delete it or archive it. But other than that, like most of those multi-branch approaches just cause extra work without that much extra benefit. So, yeah, I will give you the shirt because you are re-emphasizing the point.
Thank you.
I'm out of shirts, but that doesn't mean that you need to be out of questions. We still have 2 minutes and 13 seconds left. By the way, let me do it like this. Catch. And catch. And then catch up there and then share those stickers. Because it will be difficult to do that in here. Yeah, let's hear more questions. I don't see where the mic is. Yeah, just throw it over there.
I wanted to ask about how Git stores the really big files, because I know that for big files usually Git LFS extension is used. And what happens when that extension is used? Is that full file still stored here? Or
you mean when you say extension is? You mean like
I think
ALApp file?
Yes,
Well, I don't know if I would keep ALApps in Git, especially if you rebuild them, because then you would get conflicts which are very difficult to solve because they're happening. So one thing, like when I said that Git is fine with handling binary, and we perceive that it's not. Why did I say that? Well, Git doesn't really care what your content is. It just sees binary. But when it sees a conflict, then it will inject some text messages in there, and that's what breaks the binary stuff. So Git is fine with binary, as long as you can make sure that there are no conflicts on binary level. And I'm pretty sure, I'm not sure that I would really keep binaries in Git, like for apps.
Well,
there are better places.
For
like
apps, yes, but for example, for game development,
like
usually have a lot of...
well, okay, I'm not saying that, like, you can have artifacts like images, like audio files, like stuff, but then you should probably just not, you should organize your work that it never conflicts. So it is fine to have large files in Git. What is not good is changing them too often or having conflicts on them. So you should structure your workflow to never conflict out on that. So let's say you're handling images, like you have a 500 megabyte Photoshop PSD file in there, you know, that if you have 5 people modifying it at the same time, well, you are absolutely not going to be able to handle that. But if you make sure that one person can do that, then it requires some, you know, soft approach, like some, I don't know, PowerPoint, sorry, not PowerPoint, but SharePoint or some Teams or some, you know, whatever. Like, can I please just have this for me for the next half an hour, and then you do that. But yes, conflicts on binary level are a big problem. What will be a big problem is if you really have a 500 megabyte file that you have modified, it will eventually need to be pushed. And that's 500 megabytes to push. So my question is, does it really need to be there? Maybe, like, if you have those files, you can get them into your repository with some scripts from some other place which is not necessarily under Git source control. That's how I would approach if I really had a massive amount of binary files which I need to handle. Because they do cause transfer, you know, like push and pull or fetch. They will just...
but it's not also a binary file. For example, let's say, translations file for really big extension.
Well, with translations, you will definitely get issues. You will not get that many conflicts. I mean, conflict happens when you get the change by two developers on the exact same spot. And yeah, Git will sometimes, like what I prefer is keeping empty lines in Git, like between logical things. Because when you're changing something, you're typically changing one logical thing. So if I have, like, let's say table, I have a table. Some people will do field, 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 field without lines in between. I will add lines in between. Because Git is much easier to detect that, like, I add a field and you add a field. If there were no spaces in between, it will always see this as a conflict. But if there are spaces, there are circumstances under which, depending on, like, the surrounding code, it may see them as just two legitimate additions to the same spot and will not cause a conflict. So, I mean, translations are just long XML files which, are not well structured for Git. So if you change two consecutive translations, yes, you will get conflicts. But I mean, that's the life. That's just a part of work. So,
thank you.
Yeah, you're welcome. Okay, we have. Yeah, sorry. Whoop. Survived.
Why would we want to use or need to use a rebase?
Why do we need? So if we are working in trunk-based development, imagine 5 people committing to the same branch. How do you make sure that there are least conflicts possible? By alerting them of a conflict every time that you can. The worst kind of conflict you can handle is a merge commit conflict. So imagine this, like Luke commits something and Simone commits something. And there is a conflict between them. So they resolve the conflict in the merge commit. Now you want to merge, and your conflict arises from their conflict resolution. That's a nasty one to resolve. So in rebase workflow, you don't have those. You simply have very clear conflicts which are just, very obvious and very direct, like on commit level. Here, you don't know where does this conflict come from. Is it from Simone's work or from Luke's work? Because one commit has 2 parallel histories, and git diff cannot tell you the straight answer. Because how does git diff know what is causing conflict? It doesn't. There are 2 histories to consider. Whereas when you have straight line, you have 1 history to consider. But that's, for trunk-based development. I'm saying for trunk-based development, attempting to work with merge commits all over the place is just not going to work, because you will have more conflicts to handle which are not real conflicts. So in trunk-based development also, another prerequisite is that you need to commit often. You cannot work on your branch for 2 weeks and then commit. You commit 5 times per day or once per day, but not once per week or once per month. There are no long-lived branches in trunk-based development or long-lived work. So there are other problems with that, like how do you make sure you don't break things, but they are not the topic for this. But when you're working in this straight line, when you have narrow, small commits, conflicts happen not that often. Because if you, let's say, you change 2 files and commit, and Simone, before he starts working on his next change, just that git pull rebase, just gets whatever, wherever he is on top of whatever. If there was no conflict, and most likely there will not be because there was just a small commit, even though he might change the same thing that you changed. If he does that, he will not ever see the conflict. He will just see, changed, done by LN. I will just change to what I need, and done, nice and clean. With long-living branches, with a lot of merge commits, it's very difficult to make sure that you don't have to merge conflicts or resolve merge conflicts, because that's where Git is really clueless. Like, what is this history, that history? It can give you some best guess, but that's where, I often get asked in my Git courses, why do I continually get the same conflict? Like, I've just resolved that, and then I get the same one. Like, why? That's why. Like, you have merges all over the place. You continue working from your branches. You branch off your topic branches, and then if you want, no, I cannot anymore because I'm off. But I did prepare some Q&A, because if people ask, I'm ready to present. But I really have a nice flow, like what can happen when you branch off branches. Like, I do a topic branch, and then I do a subtopic branch. And then I decide to kind of, that's just a mess. When you take a look at Git commit level, at tree level, it's just unbelievable what's going on there, and it's not resolvable. So that's why I'm saying, like, if you do this and you do Git rebase with smaller focused commits, you will experience far fewer conflicts than if you just do long living branches. It's just statistics, people. Like if you create 50 commits over 2 weeks, and then you and there are 10 of you, and all of you have done 50 commits in 2 weeks, there are going to be conflicts. But if each of you does 5 commits a day, most likely you will not get, because I've just done 1 commit, a push, rebase. I mean, chances that I will hit into a conflict with you are so much smaller. Yeah. I mean, every time you need to resolve a conflict, that's just wasted time. Just wasted time. Yeah. Anything else? I see a lot of you are still here, so not hungry. You're going to get out of food. Yeah. Thank you.
I was like wondering a little bit how it works like on a file level. Like you said, like a branch is also just like a commit. Like how does Git handle like the difference between like a normal commit and like a branch? And
branch is not commit. Branch is a file that just points to a commit.
Points to a commit.
Yeah,
okay.
It's just a pointer. It's extremely lightweight. It's not cheap because of that. Branches cost. Branches create distances between you guys. So they cost in terms of possible merge conflicts, but they are just so lightweight, so impossibly lightweight. Just small, short file, 40 bytes long, contains just pointer to a commit, and that's it. So
and then if you create like a new master, like a new current state of affairs, then it creates just a new file and it's like on top or something like that.
So when you fetch, what Git does is it does 2 things. First, it takes a look at your head. It points to master, let's say. Then it goes to remote and says, okay, I want to get everything that happened on master. And then you know your SHA, where you are. That SHA has to be in history of remote. If it isn't, then somebody get pushed forced. So in most scenarios, it will just be fine. Your SHA is in their history. So everything that happened after that SHA, it just ships you those commits, those blobs. And then it also ships you heads, like all the branches that are on there. And that's what happens. It just stores those files locally for you so that you know what are other ones. Yeah. Whoop. Okay, I think, or are there any? Okay, there's another question. 2 questions. Yeah, thank you.
How would you deal with confidential or sensitive data that has been pushed to a repository and committed, of course?
Well, if it's really that confidential, then I just say, like, stop your work, everybody. Just, if possible, get this repository offline so that nobody can access it, because the moment you say people stop work, everybody will just pull, because, oh, what is it so important? So, okay, just jokes aside, you Git push force. So if it's pushed, you undo, stop everybody, correct it, like you rebase it out of your, or you cherry pick it out, whatever, like there are millions of ways. Like, most likely, you will, if it was last commit, just git reset head 1, and then get it out, and then push force to kill it on the remote. Because dangling commits on remotes are not going to be fetched. So there is no chance that somebody will just fetch that. But if they know SHA, then they can. They simply create a reference to that and fetch that, and yeah. So git force. And then, of course, somebody will have a problem, because if they continued working and you have forced some other history, then they will just have to kill that branch and then refetch that branch, and then maybe just replay or rebase, or there are things to do, but this is how. Yeah.
Thank you.
You're welcome. There was another one. Yeah.
So how would you deal with deployment from one trunk base into different staging systems? Like you have an internal with
I
the
would
newest
have different pipelines. I probably don't need different branches. Maybe I do. I'm not saying it's wrong. I'm just saying it's probably far more work. So depending on what exactly you are doing, like I can imagine that when you are deploying to multiple different systems, you're probably supporting multiple different runtimes, like 18, 19, 20, whatever.
No, I mean different code versions. Like you have the production for the customer, then you have a release for the customer to test new features. Then you have an internal test to
Yeah.
test the newest developments that the customer shouldn't get.
Yeah. So there are concepts in CI and CD, which, like for example, you have things called canary release. You have things called like dark launches. You have things like feature flags. So if you have one trunk, then you can control with feature flags. Like you build all your code, but not necessarily everybody can have access to that code. So there is a feature flag with which you can control if somebody can use that or not. Like that's what Windows does all the time, or Visual Studio Code, or Business Central for that matter. Like you will get code released. This is called dark release, where code is out there, just you cannot use it until you, as the owner of that code, like flip the switch and enable that code so that it suddenly becomes active. But that is one of the ways. Like you don't do it on branch level, because branches are an obvious way, because they seem the easiest. Yeah. But the problem becomes like when you have, like you as a developer do a change, and then somebody else on your team also does a change. And then if you run into conflict and you need to deploy this to multiple branches, it can be easily multiple conflict resolutions. And especially if you don't have a very clean flow, like I must first merge here and then here and then here. And if somebody just merges there before going here and there, and then, I mean, that will be a mess. It can work. I'm not saying it doesn't or whatever. I'm not criticizing people who do it like that. I'm just saying that I strongly recommend that you try a different approach. You read how other people do that. And that's all. I mean, with branches, it is always more work. In the end, it always ends up being more work. Maintaining different branches, making sure there are fewer conflicts. It's not easy. So, yeah, that's it. I think we should end. Thank you very much for your attention. Enjoy the rest of the conference, and yeah, see you around.